Continue our conversation. So we've mastered the frequency spectrum. We know what's our lowest frequency, our highest frequency. We know how to solve this now in Mathematica, but let's go ahead and finish off this problem. And instead of the frequency spectrum, let's calculate the Fourier series. So let's look at this equation that we're dealing with right here. So we need to provide an equation YF series. So let's go ahead and calculate that out. Now here you see it in this kind of general form n omega t, but we know that we could rewrite this fairly easily, right? Because we know that omega equals 2 pi f. So if I rewrite this, let's go ahead and confirm that value, omega. So let's go back to our fundamental, one of the key expressions, omega equals 2 pi f. We just saw previously. Let me go back here. Oops. Omega equals 2 pi f. So we could plug in for that value, again, knowing that our fundamental frequency, our delta f, is number t, and we could just write this as the sum of our old friend 2 pi and t over t. So that's what we're going to do in our Mathematica notebook. So let's go ahead and calculate our Fourier series. So that is going to be equal to a naught divided by 2. And then now we are going to do the sum. So the sum is going to be a total. We've worked with this function previously. And we're going to create a table of our a sub n. Actually, let's look at our a sub n. This is our a sub n expression, just to remind ourselves. So a sub n times our cosine 2 times pi times n times t. And then we're going to do this table. We're going to close that. I really don't like having the total here first. So let's do a table first, because we need to do the sum. So table of this, actually this, plus my b sub n times my sine. Again, this plus or minus, it'll just be determined by the sign of your harmonic coefficient. So sine of 2 times pi times n times t. Oops, I've got a mistake. Got to divide that by your period t. Divided by t. And here we go. So we're going to add that and that. And we want to iterate this from n goes from 1 to 10, first 10 harmonics, and we just need to make the total now. So the sum. So actually, let's pull out this value. So Control C. So again, that's going to be, if I just spit that out, it's going to be this, but we want the total, the sum. Oops, excuse me. So it'll give us a singular value. Or not a singular value, but not a list value. That's all we're doing. So we're just adding that together. So total here. And that's about it. So that's going to be our YF series. So now I can take our YF series, and actually, instead of repeating that as a variable, I'm going to paste this in here. I'm going to actually keep a lot of this same plot procedure. Actually, we're going to disappear for a second. So sorry, OneNote. So instead of list plot, I'm going to do plot, and I want to plot my Fourier series, which is this whole thing here as a function from t goes from 0 to, let's say, 5 pi. Let's see how it looks like. Ooh, I don't want to have the filling, so I'm going to get rid of that. And instead of red, I want to make this my blue. I have my thickness. Thickness be 0.05. Like this. So this doesn't have much context, so I need to actually plot first. So I want to plot several different functions here. So I want to plot my original function, so that square wave. So I'm going to plot 10 goes from raise t from 0 to pi. I'm just going to make this as plot style red. So I want to show, I'm going to repeat this times. So it goes from then 20 from pi to 2 pi. And I'm going to go to just to 4 pi. So from 0 to 2 pi, and then it repeats from here. It goes back to 10 from 2 pi to 3 pi, and then from 3 pi to 4 pi, you guessed it, 20. Exhilarating. But it'll be really cool in a second. There's really some nice analysis that can be done, so I do not mean to minimize the importance of the Fourier series. We're going to get into some fun examples too coming up. So I'm going to go ahead and grab this. I'm going to create this. Actually, I'm going to do this my YT. This is going to be my Y series. And I want to show my Y series versus my YT. And this is a pretty good match. Now, but you can see there's kind of some overshoots and undershoots because this is a function of just 10 harmonics. What happens if I do it to 50? 50 harmonics. I get a lot better. What if I just do 2 harmonics? That's not great. So you can see, as I increase the number of harmonics, as I increase the number of harmonic coefficients in my Fourier series, I could better approximate my signal of interest. So 10 is a good fit, 100 is great. Question is, for your particular application, what's the resolution that you need? So like that's the key question with this Fourier series. So it's not only just your frequency spectrum, it's obtaining this Fourier series as well. So is that important for your application or not? That's the question that you want to answer. So on the left, n equals 10 harmonics, pretty good fit. Increase, much, much better fit. So for certain applications, especially electrical, if you're trying to approximate that signal, you're going to need many harmonics. So next time, we'll do another example, integration by parts. Luckily, we have Mathematica available, so we don't have to remember that math, but it's always helpful to do so anyways. And that's going to be it for continuous Fourier transforms. And we're going to move on to discrete Fourier transforms next. So I'll see you all next time. Thanks. Bye.